10.5 Lesson 3, Area of a Polar Region. Our objective for today is you'll be able to write a definite integral to find the area of a region bounded by a polar curve. We're going to look at 3 examples, and vocabulary that we have is radial line. The 3 problems that we will work on today are find the area of the region, 11, 13 in example 2, 11, the interior of the curve given by r is equal to 1 minus sine theta. Number 13, the inner loop of the curve given by r is equal to 1 plus 2 cosine of theta. And example 2, the region between the inner and outer loops of the limacon given by r is equal to 1 minus 2 sine of theta. So the instructions are for you to find the area of the region. In our lesson today, we will write the definite integral, or a combination of definite integrals, to find the area. And I will leave the evaluation of each definite integral to you. The evaluation would be done similar to what you saw in the previous lesson, where you may have to, for example, use a power reducing formula. Let's look at 11. Find the area of the region. The interior of r is equal to 1 minus sine theta. The first thing you should do is you should look at the graph of this polar equation. So here we have the graph of the polar equation, r is equal to 1 minus sine theta. Let's take a look at this on Desmos. You can click the link that you see on the upper right corner of the screen now, and we will come back and discuss some of the things that we learned from looking at this using Desmos. So as we saw with the Desmos demonstration, we have this curve, and this is the graph of the polar equation, r is equal to 1 minus sine theta. And we have these, if you make a table where you have theta and r, and you choose input values for theta such as negative pi over 2, 0, pi over 2, pi, 3 pi over 2, and 2 pi, you'll get these values for r. Sine of negative pi over 2 is negative 1, and 1 minus negative 1 is 2. So you have this point with polar coordinates r theta, which would be 2, negative pi over 2. And then you have the point here, which would have theta polar coordinates r theta, where r would be 1 and theta would be 0. You have this point here, r would be 0 and theta would be pi over 2. This point has coordinates, r would be 1 and theta would be pi. Back here, you could assign this same point alternative coordinates, where r would be 2 and theta would be 3 pi over 2. Because remember, in polar coordinates, you don't have a unique representation for the coordinates of a point. So if you want to find the area of the region that's bounded, that is the interior of this polar curve, you have different options for writing the definite integral. One option is to recognize that you have symmetry. You can write a definite integral that would give you the area of half of the interior and then multiply that by 2. So if you want to do that, one option that you have is you could consider the region that I shaded in green as being bounded by your polar curve. Let's go ahead and shade that and highlight that using red. So now you have to consider the limits of integration. What are the radial lines that formed this particular part of the curve, or the boundaries? So the radial line would be, we start at theta is equal to negative pi over 2, which I'm showing you with the dashed black line, or the dashed black radial line. And then we have, let me show you this in gold, the radial line theta is equal to pi over 2. So if you do that, then this is what you would write for your definite integral. So this is the integration formula that we use to find the area of a region that is bounded by a polar curve, and we talked about what the limits of integration should be. Our limits of integration will be from negative pi over 2 to positive pi over 2, giving us the right half of our polar curve. And so we would be finding the area of the region that is shaded in green, but we're actually interested in finding the area of the region that is shaded in green and that I am now shading in blue. And those two regions are congruent, having the same area. So write the definite integral for the area of the green region and multiply it by 2 to get the area of the interior region for the curve bounded by r is equal to 1 minus sine theta. So what am I going to write for the definite integral? I'm going to write the following. And let me write it down here at the bottom. We're going to write for number 11, the area is going to be 2 times, because we're using symmetry, 2 times, and for the definite integral you write 1/2 times the definite integral from negative pi over 2 to positive pi over 2. And the integrand is really simple. You take your polar equation and you square it, and you have integration with respect to theta. So you're going to have 1 minus sine theta. You have to square it, and you have integration with respect to theta. This would give you the area of the region that we're interested in. And of course, when you multiply 2 times 1/2, you get 1, representing the area of the green and the blue regions, which is what we want. How would you evaluate the integral? You would have to use FOIL to multiply the integrand, 1 minus sine theta times 1 minus sine theta, and then you will have to use a power reducing formula. But you can go ahead and do that on your own, and now we're going to move on to our second example. Find the area of the given region. The inner loop of r is equal to 1 plus 2 cosine theta. You've got to look at the graph first. So let's look at the graph of this polar equation. So we want to find the area of the inner loop of this graph. This particular curve is called a limacon, and the inner loop is right here. This is the inner loop that I'm now tracing in green, and we want to find the area that is bounded by the inner loop. So that I'm going to show you in gold now. So how do we find this area? We're going to use the integration formula for finding the area of a region bounded by a polar curve, but the important thing is you need to figure out what the limits of integration are. And we'll come back to this sketch after we take a look at this particular graph on Desmos, and you can click the link on the upper right to see that. So we saw with Desmos how the particular curve is traced, and you can see from my table of input and output values to the left that we have these polar coordinates. For example, r theta, where r is 3, r is 3 and theta is equal to 0. And here we have r theta, where r is 1 and theta is pi over 2. And here we have r theta, where r is 0 and theta is 2 pi over 3. Here we have r theta, where r is negative 1 and theta is pi. And then we once again arrive at the pole when we have r theta, r is 0 and theta is 4 pi over 3. And then we have r theta, where r is 1 and theta is 3 pi over 2. So there should be a 1 here. And finally we have r theta, where r is 3 and theta is 2 pi. So the point that we made in the Desmos demonstration was that the inner loop, whose area we're interested in, is bounded by the radial lines. Theta is equal to 2 pi over 3. So here's the radial line. Theta is equal to 2 pi over 3. And the polar curve, whose graph is traced in green on the diagram here, until we get to theta is equal to 4 pi over 3, which I will show here. So these two radial lines, theta is equal to 2 pi over 3, and theta is equal to 4 pi over 3, together with the green portion of the curve, bound the inner loop. Now, on this interval, the r values are entirely non-positive, so our integration formula is valid, and we may write an integral that would give us the area of just the inner loop. You could also use symmetry. If you were to do that, you could use the radial lines. Theta is equal to 2 pi over 3, and theta is equal to pi, which would be right here. And of course, if you consider the opposite ray from the radial line, theta is equal to pi, you would have the bottom half of the region, the inner loop. And you could multiply that by 2 to get the area of the entire inner loop. So there are different options for the limits of integration. Let's take a look at one of them. So suppose you just want to find the area of half of the inner loop and multiply by 2. So if we do that, we're going to have to write area is equal to 2 times, and the integration formula for finding the area of a region bounded by a polar curve is 1/2 times the definite integral from alpha to beta, and our limits of integration for the bottom half of the inner loop will be from theta is equal to 2 pi over 3 to theta is equal to pi. And the integrand is the easy part. You just take the polar equation, 1 plus 2 cosine theta, and you square it. And there you go. That will give you the area of the inner loop. Of course, 2 times 1/2 is 1, and this is what you'll have. Now, how do you evaluate this definite integral? You need to do FOIL here, and you will get 4 cosine squared theta as a term, and you have to use a power reducing formula and then go on from there. Let's take a look at the next problem. This is example 2 from your textbook. Find the area of the region lying between the inner and outer loops of the limacon. R is equal to 1 minus 2 sine theta. With all of these problems, you have to begin by looking at the graph. So let's look at the graph of this polar equation. So here's the limacon, and we want to find the area of the region that's lying between the inner and outer loops of the limacon. In other words, you've got the inner loop here. This is the inner loop that I'm showing you in green. And of course, we know how to find the area of the inner loop. It's similar to what you saw in the previous example. So you would find the area of the inner loop. But that's not what we want in this problem. We want to find the area of the region lying between the inner and the outer loops of the limacon. So where is the outer loop of the limacon? Let's go ahead and trace it using black marker. You can see this is the outer loop of the limacon. So if I find the area of the region bounded by 2 radial lines and the black part of the curve that I just sketched, this is what you would see. So this would be one radial line, and this would be the other radial line. And this radial line would be theta is equal to 5 pi over 6. And this radial line would be theta is equal to 13 pi over 6. And the region bounded by the polar curve and these 2 radial lines would be the region that would be bounded by the outer loop. But what we want is the area of the region lying between the inner and outer loops. So we want the difference of the area of the region inside the outer loop and the area of the region inside the inner loop. And when we find the difference of those two regions' areas, we're going to get what we want in this problem, which would be the area of the region lying between the inner and outer loops of the limacon, which I am now shading in red. So we already talked a little bit about the limits of integration, and we're going to look at this using Desmos, and you can click on the link on the upper right, and then you can come back as we continue with our discussion here. So our problem will require us to find the area of the region bounded by the outer loop, area of region bounded by the outer loop, and subtract from that the area of the region bounded by the inner loop. And that difference will give us the area of the region lying between the inner and outer loops of the limacon, given by r is equal to 1 minus 2 sine theta. When you write a definite integral for either of these two areas, the most important thing is to get the correct limits of integration. And for you to understand what the correct limits of integration are, you can understand the theta value at which the inner loop starts to be traced, and that is at theta is equal to pi over 6. You have this point at the pole with polar coordinates r theta, where r is 0 and theta is pi over 6. And then here you have this point r theta, where r is negative 1 and theta is pi over 2. And then you complete the inner loop when you get to theta is equal to 5 pi over 6 and r is 0. And if you wanted to use symmetry, you could. It's an option that you have. You could go from theta is equal to pi over 6 to theta is equal to pi over 2, and then you would just be considering the half of the inner loop that I just shaded in blue, multiply that area by 2 to get the area of the entire region within the inner loop. So those are options that you have. Or you can just integrate from pi over 6 all the way to 5 pi over 6, and that would give you the region that is bounded by the inner loop, and you'd get the area of the region bounded by the inner loop, all of it, not just half of it. So if you wanted to do that, let's go ahead and do that. Replace the words in green, area of the region bounded by the inner loop. That's going to be given by this definite integral. So we're going to have 1/2 times the definite integral from pi over 6 to 5 pi over 6. And what is the polar equation for the curve that we're looking at? It's 1 minus 2 times sine theta. So we have 1 minus 2 sine theta, and we have to square it, and you have integration with respect to theta. Now we have to write the definite integral for the area of the region bounded by the outer loop. So let's go ahead and do that over here. And of course you have to subtract those two to get the area that you really want, which is the area of the region lying between the inner and the outer loops, shown in red in my diagram. So for the area of the outer loop, the black part of the limacon is traced as theta goes from 5 pi over 6 to 13 pi over 6. So you're going to write 1/2 times the definite integral from 5 pi over 6 to 13 pi over 6, and the integrand would be the square of the polar equation. So 1 minus 2 sine theta, you square that, integrate with respect to theta. And then find the value of each definite integral, and subtract the values of the two definite integrals to find the area of the region lying between the inner and outer loops of the limacon. And of course, to evaluate each definite integral, you would have to FOIL, and you will have to use a power-reducing formula. Today we took a look at these three problems: find the area of the region, and our objective was you'll be able to write a definite integral to find the area of a region bounded by a polar curve. And as you saw with all three problems, you had to begin by looking at the region, by looking at a graph, and then you had to focus on finding the limits of integration. And that has to do with understanding, for your region of interest, which part of the polar curve bounds it, and what value of theta starts that part of the polar curve, and what value of theta ends that part of the polar curve.